Hello, everyone. Welcome to this session. Today, let me introduce myself. So I'm Izaak Meckler. I'm CTO and one of the co-founders of O1 Labs and one of the co-initiators, shall we say, of Mina. And today I'm going to be sharing a bit about kind of the architecture for snaps on Mina. You might be asking yourself, what are snaps? You keep saying this word, but what does it mean? Well, let's first remind ourselves what is dApps. So, let me also add, before I get too much further into it, Vanashri, lead cryptographer at O1 Labs, is also going to be helping out with some questions in the chat and later on. So, So what are snaps? Well, let's first talk dApps. dApps is an application. Okay, right, that's the app part, with public data, usually, censorship-resistant execution, and that's pretty much it. So that's kind of what defines the dApp. D, it means decentralized. I guess that refers to the fact that there's censorship-resistant execution, basically. Snaps are applications with private and or public data, so could be private, could be public, also with censorship-resistant execution, but they add a few things. So the first is this kind of universal verifiability, so anyone can check that the snap is operating as expected. And two is scalable execution. So the application can sort of handle a large amount of usage without sacrificing the censorship-resistant execution or the verifiability. And in this talk, I'm basically going to be covering the model for the snap execution environment, which is currently under development for Mina and operating in a testnet. So let's kind of first start by just covering what is the transaction model of snaps. And the idea is basically a snap transaction is a sequence of, bear with me, okay, authorized, predicated updates to accounts. And what are these updates? It's stuff like changing the balance, changing the nonce, changing some state in the account. But this is all very confusing. You know, what is authorization? What is a predicate? Blah, blah, blah. So let's just take it kind of one step at a time and just start with the updates. And we'll just like kind of add these layers of qualification on top of it with the predicates and the authorization. So as a first attempt, let's just say that a transaction is a sequence of updates to accounts. What kind of updates? Well, balance change, nonce change, etc., and more we'll see later. And this will be our first working definition of what a transaction will be. To make things really concrete and give an example, here would be an example of a transaction. That is a sequence of updates. It would consist of two updates. This is a simple payment transaction. The first update, it has sort of the identifier of the account that it operates on, the public key and the token. And it modifies the balance. It decrements the balance by 10. And it increments the nonce in that account by 1. And then that's on the sender side. And then on the receiver side, we see, again, you have the account identifier, the token, and the public key. But then we also have the balance increment. Okay, so this is like two updates, right? Update the sender account in this way, update the receiver account in this way. I hope that's clear. So let me just elaborate a little bit on this idea of a sequence of updates to just give an example of like what a token swap transaction would look like. So there's two tokens. There's the Mina token, and let's say there's the ABC token. And these two parties are trying to swap some Mina for some ABC. So this public key B62QNSUBG, they have some Mina. This other public key B62QPEMJ7, they have some ABC, and they're swapping. So how do they swap? The first person's, their Mina goes down. The second person, their Mina goes up. The second person, their ABC token goes down. The first person, their ABC goes up. Okay, so that's a swap. But there's a problem with this because we need some kind of authorization, right? We don't want to just allow anyone to update any accounts. There needs to be some kind of authorization. And probably everyone knows how do you authorize with signatures. So here's like the kind of raw transaction of updates. But then you have to add some authorization. So each update has some authorization attached to it. For the senders, we have signatures, and for the receivers, we have nothing. There's no authorization needed to receive funds, typically. We can now amend our definition and say that transaction is a sequence of authorized updates. And this will be our new provisional working definition. Okay. A sequence of authorized updates. Okay, fine. But actually, if you're thinking, this is not enough either, because this can just be replayed whenever, right? Let's say I make this transaction, right? Okay, now I want to just repeat it. I can just broadcast it again. Say, do this again, do this again, do this again. And of course, we don't want that, right? No one agreed to that. What we need is some kind of predicate which constrains application. What do I mean predicate? I mean some kind of condition that we check at sort of transaction application time, and only allow the transaction to go through if the predicate is satisfied, if the condition is satisfied. So what is the condition? Well, it's that the nonce is a specific value, and that for both parties engaging in this transaction. And what this will do is, because the updates increment the nonce, it will mean that once this transaction is applied, actually it will never be applicable again, because the nonce is incremented, and so that's that. So we can now come to our perfected final definition, which is that a transaction is a sequence of authorized and predicated updates. So a sequence of updates, each of which has some authorization and some condition, which must be satisfied in order for the transaction to go through. And just to kind of, really drive things home, just make sure everything's completely clear, let's just go through for this example of a swap or a payment. What is the authorization? It's the signature for the senders and nothing for the receiver. What is the predicate? It's the nonce equality check on the sender, nothing on the receivers. And what's the update? On the senders, we decrement the balance, we increment the nonce. And on the receivers, we increment the balance and don't touch the nonce. Okay, so that's that. All right, so this is sort of a very generic setup. Obviously, these are specific authorizations, specific predicate. So this is not, I said nothing about snaps so far. This is just sort of normal transactions. So how would snaps be different? It's in the choice of data for these three things. So for the authorization, we now make it possible not just for a signature to be authorization, but actually a SNARK proof to be authorization. And for the predicate, we also generalize that. So it's not just a nonce equality check. It's a range check, so checking that a value is in a particular range, or an equality check on any field in an account or in the blockchain state. So things like current block height, current balance, whatever. Say, this transaction can only go through if the current block height is between 1,000 and 1,010. And what is the update? Well, the update will be sort of arbitrary updates to any fields in an account with some constraints. What are the constraints? First of all, balances can't go below 0. Okay, obviously. So right, so we're kind of explaining now what's the snap transaction, how does it differ from a normal transaction? And I'm saying it just differs in the choice of what kind of data we permit for these three things. Right, so there's some constraints on the update. It's not totally arbitrary, like total balance change can't be has to be negative. So you have to be not creating money out of thin air, unless the account is a sort of a permission to do that. And right, and in general, sort of updates have to be permitted by an account's permissions. So that's all very nice. I mentioned that there's some fields. I said arbitrary updates to fields. Let me just be specific about what those look like. In a standard account, which is running on Mina right now, you have the following data. There's the public key, there's an ID for the token, there's the delegate, there's the nonce, there's the balance. There's actually a little bit of extra data too. A Snap account has all of the data of a normal account, plus a few other things. It has a verification key. So that controls what SNARKs are allowed to sort of authorize updates to the account. And it has an application state. And the application state is an array of field elements, currently 8. It's subject to change, okay? And that can be used to hold whatever data that the application might need. And we'll see a few examples. So let's do a really silly example just to make sure that we understand things well. So how is this silly example going to work? So we're going to have an application, it's an account that you can only move money out of on Fridays and only once per Friday. And anyone is allowed to move money out of it. It just has to be Friday. And it has to be the case that no one else has moved money out of it on this Friday yet. I hope that makes sense. It's sort of this is like a who can get the first transaction in to take money out of the account every Friday. I guess that's the game. Right, so remember, we have our authorization. So here is the authorization. It's a proof. It's going to be a proof that has to verify against the verification key stored in this account, VK1. So it's going to be against the verification key VK1, this proof, and it's going to accept the whole transaction as input. So the circuit that is hiding behind VK1 is going to be able to consider the whole transaction and think, do I want this transaction to go through or not? So let's unpack that a little bit. How is VK1 going to make that decision? Well, let's just take a second to look at this transaction. So we have the proof, fine. We have the sort of originator information, the sender kind of information, this token Mina, public key, SUVG, whatever. Then we have the predicate, remember, res predicate. What does the predicate say? It says the current slot has to be between 4,460 and 4,940. The current slot is kind of like the current time. And I looked it up and I made sure that this is a Friday. I think it may have been last Friday. So it says, I'm currently being applied on Friday, on a particular Friday. And the current state, 0, should be equal to 1100. 1100 was a slot that was a week ago, okay? So it's saying, I can only be applied if right now it's March 26th, and state 0 is equal to a slot that occurred on March 19th, last Friday. And if all that's the case, then do this. Subtract 10 from my balance and set my state 0 equal to 4460, the slot that's at the beginning of today's Friday. And then send that 10 to this other person, B62QPEMJ, whatever. How we need to be able to encode that logic that enforces that the only proofs that are going to verify against VK1 are ones that sort of do the right thing Friday-wise. Yeah, so we want VK1 to do the following. We want to accept the transaction that is provided as input if the following is the case. The predicate constrains the current slot to be on a Friday, and that's something we can check because we can take the current slot, we can take the remainder mod, or maybe we divide it by the number of slots per day, and then, we sort of take the remainder mod 7 or something. We can see whether actually the current slot predicate says today's Friday. And VK1 will enforce that state 0 should be at least 1 week in slots before that. And that's also something we can check. It's just, check the difference between this number and that number is at least whatever the 1 week, however much 1 week is, 3,000 something. And VK1 will also say the update must do the update part of the transaction must do the following. It must set state 0 to the beginning of the interval that was specified for the predicate. So the total effect of this is you can only transact in this account if currently it's Friday and the last time the account was touched, which is recorded in state 0, was at least a week ago. And so that's a silly example. I hope that makes sense. Right, so this was the example. Here was the transaction. We had these two parties, the sender and the receiver. And moreover, I want to stress that a lot of privacy could be added to this example. Okay, how? Well, for one, we could make the verification key private. We could change this application, and actually will sort of be this way by default, which is no one will have any idea what is the logic governing this account. That will be totally hidden, and maybe that's a good thing. Maybe you don't want anyone to know that this is an account that you can move money out of on Fridays. Of course, they could try maybe for themselves and see if they could try and figure it out, but actually they wouldn't really be able to. So that's one. The other thing is you could hide the state data. So that could also be totally sort of encrypted, not exactly encrypted, but something like encrypted. And in that way, when someone saw this transaction, all they would see is, oh, there's some snap transaction. It's being, constrained to be applied in some slot interval, and it moves 10. But the actual logic of the sort of state transition and the logic of the thing would be totally hidden. And just to kind of emphasize this a little bit, the other thing is, so each Snap account is basically like a little state machine, okay? But, and this is sort of, you can imagine a bunch of Snap accounts, little state machines in all of them. And the state transitions can be conditioned. The programmer can specify this state transition is only permitted if you demonstrate this kind of knowledge or this kind of computation. For example, that today is a Friday and blah, 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 blah. And furthermore, these state machines can talk to each other. So you can also sort of condition transitions on other transitions occurring in other Snap state machine accounts. So it's really kind of a full-featured, smart contracting sort of system for controlling these little state machines, which are running inside of these little mainnet accounts. And furthermore, these state machines are optionally private. So, for example, the state can be hidden, or like in this case over here, where the state is hidden but the logic is public, or the state can be hidden and also the logic can be hidden. So you can totally the only things that are public are sort of which other state machines is it talking to, and the balance also. The rest of the talk, I'm going to be describing some example, a more fleshed out example, and also previewing a little bit or teasing a little bit maybe what's kind of coming up. But I just want to take a moment to pause and discuss this example, this invention, which is, I think, really remarkable. So I think there's like a common belief in this industry, and I think, it's not anyone's fault that they believe this. I think there's a lot of pressures that cause it to be the case that people have to think this way, which is that technology can determine social relations, or in other words, you can sort of restructure society or how people relate to each other or something purely through technology. I don't think that's the case at all. I mean, maybe occasionally that happens, but very rarely is that the case. And sometimes, so sometimes it can sort of do that, but more often than not, it's a lot more affected by the other forces. And so I think this is a really good example to keep in your mind for that. This is called what's called Aioli pile. Okay, this is basically a steam engine, which was described by a guy named Hero in Alexandria in the 1st century AD, so like year 50 or something. So they invented the steam engine, but as we know, it's not like they had an industrial revolution in ancient Alexandria. And the reason, some speculate, is they had no need for this because they had a lot of slave labor. They had a system of slave labor in their society, and their society was not organized around the idea of unending growth of productive capacity. So there wasn't really any use for this thing. They had plenty of labor to go around, and there was no constant demand for increasing productive capacity. So I think this is just a really good example to kind of keep in your mind as like an example of the fact that technology does not, it's the social relations, above all, that determine the impact that a technology will have. So let's just keep that in mind. We're always usually describing examples and applications that pertain to the social relations which are dominant in our current society. And that's because, people want to give people something that they can go and maybe build right now, or describe some system that some company will implement in the future, in the near future or whatever. But I'm not going to do that right now because I think it's more fun to try and imagine different social relations and give an example of an application that I think could be used in such a situation. So here's an application for a future society. Okay, so let's imagine a society that has housing set up in the following way. We want to say, if it's the case that you're not currently living somewhere and there is a residence, like this one here, that currently is unoccupied, then you can start living in that residence. So that's how housing will be set up in our future society. There's no private ownership of housing, there's no speculation, etc. What are we going to require for such a system? There will be two components. One will be some kind of device that controls the lock on the apartment. What does it mean to own an apartment? I guess it means you control the lock and other people hopefully don't come in. And then there will be like a Snap account that maintains some state about an individual resident. Okay, and there will be a key, a verification key in that account, resident VK, which will sort of govern the logic of this little state machine of this account. So let's just dig in a little bit to what's in this device. What's the state that's in this device? This will be state which is local to the device that controls the lock. So it's not on any kind of blockchain. There will be a key pair, secret key, public key, SKA, PKA, and there will be some state recording what is the public key of the current resident. So it's either public key of someone or it's not. Okay, and then what's in the Snap? There's going to be a a privacy-preserving commitment, kind of like a hash of a list of attributes about that person. For example, a list of attributes that says house public key, the public key of the house that this person is currently living in is da 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 da. But none of that is visible on chain. It's private because it's a hash, okay? What's the flow kind of for moving into a new place? First, you move out of your old place. You send a snap transaction setting house PK, this house PK in your account to null, although no one sees that. They just see that you've changed the hash. And then you tell the house, that you're trying to move into, that you'd like to move in, and you prove to that house, that little Mac icon computer, that your current house PK field is null. So that's how you prove to them, hey, I'm not, I don't have a house. Then the house sort of outputs a signature saying, yep, I'm good, I'm unoccupied, and you are approved to move in. And then you send a snap transaction setting your house PK field to that new house's public key. So just to kind of illustrate this a little bit, at the beginning, the local state would kind of look like this. This is if you're living in this house with PKA. Your Snap account would have PKA inside of it. And the local state of the machine governing house A would have your public key, PKX, inside of it. Then you move out. What happens? The resident becomes null. Your house PK becomes null. Let me just kind of step through a little bit how the state machine looks, just so you can see this is, I think, a nice example of how the Mina blockchain plus like some devices interacting with it can make kind of a cool system. The state machine will look like this. Okay, the state has the keeper and the resident. Okay, the keeper is never going to change. The state works in the following way. If you input a signature from PKX on the message, I'm moving out, and PKX, is equal to the current resident, then set the current resident to null and output a signature from you that says, yep, this person moved out, I approve. And then if someone wants to move in, what do they have to provide? They have to provide a signature from their new public key. This is a new guy, Y, on the message, I'm moving in, and a zero-knowledge proof that the on-chain commitment, the on-chain hash corresponding to PKY's account has house PK set to null. So it proves, hey, here's the current Mina state, which you can get from the internet. And if you look inside that state and you look inside my address, actually, I can prove to you that I'm currently, I set my housing address to null. And then the device will say, okay, looks good to me. You're all good to go, and issue a signature that says you're moved in now, and set the resident to PKY. And just to remind you, this is all kind of running on this little machine that's like attached to the house or whatever. So how does it look from the point? So that's the same machine like on the local device. How does it look from the point of view of the Snap, like running on Mina? This is the Snap sort of corresponding to resident PK. Well, there's the following situation. If you're in a situation where your state says house PK equals null, and you can provide a signature from some public key PKA on the message, PKX has moved in, then you are allowed to update your state so that now house PK is PKA, and then that's moving in. And then what about moving out? Well, if you can provide a signature from on the message from PKA on the message PKX moved out, then you're allowed to set your house PK to null. So in that way, we kind of make sure that these two state machines are totally in sync. And just a reminder, this is happening on the Mina chain. So I just want to take a second now to kind of step back and appreciate some patterns illustrated by this example. So the first is using commitments for the privacy of on-chain data. So in this way, we can have some data that lives on the chain, but is hidden, okay? So no one knows what your current house public key is. They just see basically a hash, okay? And the second is use of on-chain data to interact with off-chain processes that access the Mina chain directly. So this is really kind of where the succinct blockchain like really kind of shines, which is that these, you could have off-chain devices that are able to synchronize to the current chain and say, yep, you're really approved of this. So, right. Let me just take a second to just like remark on this. Obviously, this could have many dystopian uses as well. That goes back to my point about social relations determining the application of technology. We can imagine in our current society that this would be used to lock people out of their houses if they don't, if they're not good tenants or whatever. So let me just comment now, and then we'll go to questions about some work that's currently under active development that I think is very exciting. So this is what we're sort of provisionally calling HTTP snaps. So it's like HTTPS, but snaps. And this will basically allow importing data data from websites basically onto the Mina chain and to use in applications. So for some reason, silly examples help me understand how the thing works, like my stupid example before of the Friday account. So let me just give you a silly example of something you could build with this. I really hope we have better ideas than this, but this I think will make it stick. A silly example is you can make a Snap account that has maybe some tokens in it and would let anyone move money out of it if they prove they produced a tweet that had at least 10,000 likes that contains the word pizza. So you could have sort of a decentralized marketing campaign for pizza. And then just a comment before I end and go to questions on kind of looking forward. So there's this HTTP snaps work, which is in development now. Shout out to everyone who's working on that. Vanashri, Vitali, Joseph, Dan, Matthew. I'm excited for how that will develop. And then there's the Snaps Developer SDK, which is also under development, and we'll have more to say on later. And yeah, with that, I will say thank you for watching. And let's see, I'll see if there are any questions. In the Friday example, the next state 0 must be exactly 1 week later rather than at least 1 week later. Otherwise, you have a DOS attack. No. I say no, maybe not, because you update the state to the slot at which the transaction was applied. So if a transaction goes through, then it needs to be at least 1 week later before it can be applied, before another one can be applied to that account. How does Mina resolve the decentralization problem? It looks like Vanashri has given a good answer to this. Are there plans of bootstrapping Snap development through hackathons and or something like an incentivized testnet? So let me not comment too much on that. We will certainly be having some kind of Snap development program. I look forward to kind of sharing more about that in the future. Would adapt like Uniswap be deployable on Mina? So Vanashri says yes, and I will just echo that. Yep, you can implement something like Uniswap. We actually this is a great example because we actually tried to spec out like if things like that. How many people work on Mina? You can find info there. Sure. So is a state machine validating SNARKs? So yes, basically each state machine, in order to transition that state machine, you need to provide a SNARK. The advantage of being 22 kilobytes. So okay, well, I won't say anything about this 22 kilobytes thing because it's actually, I think, slightly smaller, but I probably shouldn't say anything about that. The advantage of being really small, like 22 kilobytes, for example, is that any application, even with a crappy internet connection, can easily, any device can easily sort of get that data and then verify that data and interact with that, interact with the chain directly in that way. Okay, it's 11 kilobytes. Otherwise, join us in the Discord, please. I'm sure the Discord link has been posted many times, but if you just go to our website, you can easily find the Discord, minaprotocol.com. It's there. And otherwise, follow me on Twitter, follow us on Twitter. We'll obviously keep tweeting about this. So